Hi, my name is Vittorio Nazzi and my Z ID is Z5718300. So let's dive right in. What are Kepler's laws? Well, Kepler's laws describe how planets move around the sun, and there's three of them. So the first one is the law of ellipses, which means that a planet moves around the sun in an elliptical orbit rather than a circular, with the sun at one of the two foci. You have Kepler's second law, which is the law of equal areas. So that means that a line segment joining a planet and the sun sweeps out at equal areas in equal intervals of time. So planets move faster when they're closer to the sun and slower when they're further away. And then we have the last of the laws, which is the harmonic law. And this is basically a proportion where the square of a planet's orbital period, in mathematical terms t squared, is directly proportional to the cube of the semi-major axis of its orbit, which is a cubed. Moving on, when we look at the planets moving in orbits, yes, in the planet-moon scenario, the planet does move slightly as the moon orbits, and this is because both bodies orbit their common center of mass, which is called the barycenter. Question 9b, what are the center of mass locations in question 1, 4, and 7? Well, in question 1, with a normal star-planet system, the center of mass is extremely close to the center of the star because the star is far more massive. Question 4, however, when the planet's mass increases, the center of mass shifts slightly farther from the star's center, but it does still remain in the star. And then when we look at question 7, when the star mass is changed, the center of mass can shift significantly. So a more massive star pulls the center of the mass closer to itself, and a less massive star allows the center of mass to move further away. How is the planet-moon center of mass different? Well, the planet-moon barycenter is usually inside the planet because the planet is much bigger than the moon. However, in contrast, in the star-planet cases, the star is so massive that the barycenter stays extremely close to or even inside of the star. So there's like the wobble of the planet around the barycenter, and it's much more noticeable compared to the wobble of the sun in the earlier scenarios. Let's move on to the distance between the grade lines in AU. So each grid line spacing, as you can see here, let me share my screen. Each grid line spacing is 7.36 up to the 10 to the power of 7. And if we divide that by 1.496 and then divide that again by 10 to the power of 8, we actually get an approximate value of around 0.49. I'm going to stop sharing my screen. And that's what we calculated as the grid line spacing. And then if we apply that to the table, we know that 0.5 AU will be an orbital period of around 125 days, 1 AU will be an orbital period of 360, 1.5 of around 650 days, and then 2 AU will be around 1,000 days. So do these results follow Kepler's third law? The answer is yes, they do. The stimulation results do follow Kepler's third law, and when you square the orbital periods and compare them to the cube of the orbital radius, the ratio actually stays nearly constant. So t squared and then 2t squared goes much faster than t cubed. And then this confirms that planets further from the sun actually take much longer to complete an orbit in a predictable mathematical way as well. For question 15, which planet has the fastest orbital velocity? Well, that is Mercury. It's the closest planet to the sun, and it experiences the strongest gravitational force and must move quickly to remain in orbit. Which planet is the slowest? Well, that's Neptune or Pluto if we count that, because they are the slowest and they're furthest away from the sun, where gravitational attraction is the weakest. And this follows Newton's version of Kepler's laws and gravitational force, where basically we said F equal to gm times lower m divided by r squared, and a planet must move with the right orbital speed, and the equation for that is velocity is equal to the square root of g, gravity, divided by mass, divided by r. So the closer the distance, the stronger the gravity and the higher the velocity. The further the distance, the weaker the gravity, the slower the velocity. And this is what we observe across the solar system, so it holds. So what did I learn in this experiment? Well, I learned a few things. First of all, I learned how motion depends on mass, distance, and velocity. I adjusted the mass of the planets and the stars, and by changing the orbital velocity, I saw how the shape of an orbit can change from circular to elliptical, for example. I also observed how both objects in a system orbit their common center of mass, the barycenter. And then by testing multiple orbital distances, I was able to kind of confirm Kepler's third laws in practice, showing that orbital period increases predictability with distance from the sun. And overall, I really enjoyed the simulation and it helped me visualize how gravity controls motions in the solar system while also connecting mathematical laws. I hope that this video was insightful, and thank you very much.